Damn! Sonic boom!
Alright, let's calm down. There are no supersonic flights flying over India right now. Although, if you want to offer me a role in your movie, I won't mind. Jokes apart, today I want to talk about supersonic flights. After the Concorde incident, supersonic flights above land were banned, and NASA wants to bring it back with their X59 flight. In this video, we will learn about why supersonic travel was banned, how it can be fixed with math and physics, and how all of it is put together in the X59. Let's learn the basics first. A supersonic flight travels greater than the speed of sound, and the Mach number is one way to represent if you are flying supersonic or not. At 20,000 meters above sea level, the speed of sound is about 1060 kilometers per hour. So if a flight travels at that speed, it is said to achieve Mach 1. In other words, if the flight flies at 2120 kilometers per hour, then it is Mach 2. Hope you see the pattern. At such high speeds, air feels like water. Just like a boat causes waves, a supersonic flight causes waves in the air. You can't see it, and they travel at the speed of sound. When this wave hits the ground, it causes a loud noise, which we call as sonic boom. Sonic boom is unpleasant. It can shatter glasses and apparently stop chickens from laying eggs. In a given day, there are over 100,000 flights that are operational. If they were all supersonic, that can really be a nuisance. It's partially the reason why commercial supersonic flights over land got banned. So how to fix this? In one word, geometry. If you take a bullet and perform some advanced imaging studies in a wind tunnel, you will see some distinct lines. These lines represent regions where air gets compressed and creates waves. These waves are called as shockwaves. This is very similar to how a boat creates waves. Now, a small wave in water does not push you, but a big wave can. Similarly, sound waves are usually tolerable, but a shock wave is not. Also, if you see this image, there is a wave at the start and a wave at the end. From the ground, this sounds like two distinct sounds. And that is the characteristic of a sonic boom. Now, technically, this is also referred to as a sound signature or a pressure signature. Why a pressure signature? Well, changes in pressure that occur over time is what we perceive as sounds, and hence it's called as a pressure signature. Now that we understand that geometry affects the shape of the waves, well, we can do something about it. And that is kind of the reason behind designing the X59 airplane in a very unique way. In fact, we can easily figure out why they made certain design decisions by using simple maths. There are simple math models with which we can predict the ground pressure signature. I used Witham's equations to generate the pressure signature. Basically, you have to do some code for this, which is not very hard. Since sound is just changes in pressure, right? You can actually convert the change in pressure data, or also called as the pressure gradient or delta P curves. You can convert that into a sound that you can actually hear. Now, you may want to use a headphone for this, but this is what you're going to hear. You're going to hear simulated sonic boom. Now, this is a mathematical model, so this is not scientifically accurate, but this is great to understand how the shape of the geometry affects the sound signature that you get when you are in the ground. Alright, so now what do we have here? This geometry represents an airplane, right? Now, the front portion of it is called as the nose, The middle portion is the body and the end portion is the tail. Now what my code does is very simple. It assigns a particular length for each of these sections, and then it solves an equation which basically tells us how the ground signature or the sound signature is going to look like. So here are the results for the base geometry. Now you can actually see that the change in pressure is proportional to how rapidly the geometry changes, right? How suddenly the shape of the geometry changes. So naturally, one intuition is to basically make gradual changes in the geometry. So how do you do that? Well, you make a really long nose. And when you do that, the geometry actually changes very slowly because the slope has been decreased. And now if you hear the sonic boom for this particular variation, note that it is considerably lower. And also, the two distinct booms are temporarily apart, meaning the time gap between them is slightly longer. This is the primary thought process behind X59's unique design, and this also teaches us to never underestimate fundamental physics and the power of first principles thinking. Now this brings us to an excellent point in engineering that occurs very frequently. We have a unique insight, right, which has been gained through fundamental analysis. Now, in order to go in that particular direction, you need to solve engineering problems that were never solved before. In this particular case, you've decided to go with a very long nose. Now, this is going to create a whole bunch of problems for which hardcore engineering is required. Since we have a long and slender nose, we need to fundamentally redesign the aircraft's inner structure. This means using new materials and new manufacturing and assembly processes. Since we made the nose ridiculously long, the pilot is no longer able to see what is in front of them. And hence, we have to redesign the cockpit from scratch, and this is going to be 100% digital. The only way the pilot is going to see what is in front of them is by having a high definition or ultra high definition camera. So now you have a flight that has a ridiculously long nose made with new age materials and new age manufacturing process. A cockpit which is essentially a ultra HD camera. What about flight safety? Especially this flight is going to fly supersonic. Well, in order to be able to do this, NASA's team has to innovate on one other aspect, which is avionics. Here, everything from data acquisition to redundancy engineering so that you have multiple backup systems for critical functionalities, right? Has to be rethought, rebuilt from scratch. While fundamental innovations are being made, we also have to save time in the build process by using existing systems that actually work. For instance, the modern turbofan engine is already capable of supersonic flight. So the X59 uses an F414 GE 100 turbofan engine. Since supersonic flight typically happens at higher altitude, the pilot needs a dedicated oxygen supply. High altitudes can cause combustion issues because the air is much thinner. Now, this means you need a backup system. The backup system uses hydrazine. Hydrazine is a highly reactive but toxic chemical, but it serves as an emergency power source for critical systems if necessary. Engineering is not about just coming up with an idea and implementing it. You have to validate it rigorously. In other words, you have to challenge your idea openly and rigorously. Given that the fundamental premise of the new design is to validate the long nose, we need to take pictures of the shockwave, and this requires special procedures. The X59 should be followed by another plane in which special imaging tools need to be positioned carefully. On top of this, a whole bunch of complicated computational simulations are performed to predict how this aircraft is going to perform. It is just amazing that the team at NASA has done all of this, and the hope is that in 2025, the first flight would take place. So that's it for this video. If you enjoy this content, consider subscribing and I'll see you in the next one.